Look at any high-frequency trading floor or global server hub. Every millisecond, billions of dollars and terabytes of data flow across these networks. Survival in this space isn't about human reflexes. It relies entirely on the precise synchronization of these machines down to a fraction of a second. If you trace the data running through our telecom grids, our complex financial algorithms, and our power networks, they share a single requirement. Every node must agree on exactly what time it is to function without collapsing. To maintain that level of synchronization, all these digital systems communicate using a single globally accepted baseline, the International System of Units Standard of Time. But there is a hidden vulnerability in this setup. The current standard is defined by measuring the radiation cycles of a cesium-133 atom. Our digital superstructure is effectively tethered to the physical vibration of a single atom. We built an instantaneous digital future, but we anchored it to a physical piece of hardware. And like any physical substance, these atoms are subject to friction, environmental changes, and ultimately total structural failure. As we push processing speeds into the quantum realm, the demands for precision increase. We are reaching the physical limits of what a cesium atom can accurately measure. Because cesium is matter, it is bound by the laws of thermodynamics. Over time, its structure experiences entropy and unavoidable degradation. This creates phase drift. At quantum speeds, the atomic vibration loses perfect rhythm, desyncing from the constant baseline. This microdrift scales upward rapidly. One delayed packet forces a resync, triggering cascading delays that cause entire data systems to fall out of alignment. When timing protocols fail, the results are concrete. Trading algorithms crash, data centers experience processing gridlock, and autonomous systems traveling at high speeds fail to communicate their positions in real time, resulting in catastrophic collisions. Physical timekeeping is a decaying infrastructure. To navigate the requirements of quantum technology, we must stop using physical matter as our primary clock. Achieving zero-drift precision requires removing fallible atoms from the measurement. Instead, we have to anchor our systems to absolute mathematical constants. This is the purpose of FTU spec version 1.7.1, or the FADE tempo unit. It is a sealed, verifiable specification designed to replace the cesium atom baseline. The FTU operates as a reproducible base tick for system architectures. It is anchored strictly to the work of physicist Max Planck and his calculation of Planck time. Planck time is approximately 5.39 times 10 to the negative 44th seconds. It is the irreducible, mathematically perfect minimum tick of reality. Unlike a piece of physical cesium, a mathematical constant has no mass and no physical structure to break down. It does not experience entropy or drift. By mapping the base tick to Planck time, the FTU replaces a piece of decaying hardware with a standard rooted in mathematical code. This flowchart outlines the FTU's theoretical framework, the axiom of frequency. It identifies frequency as the sole invariant property spanning every domain. Under this axiom, all phenomena are modulations of universal frequency. If frequency is removed, the null test suggests existence itself would cease. To map these frequencies, the framework uses the Gauss law formula, calculating system states with a critical timing variable known as TF. The FTU provides this constant value. Anchored to Planck time, the formula gains a stable quantum-level tempo. Because the tempo is locked to a physical constant, the Gauss law can normalize frequencies across a network without introducing the decay inherent in atomic clocks. The FTU provides the specific numerical anchor needed for the Gauss law to maintain mathematical precision in every calculation, regardless of the system's scale. Our current infrastructure runs on a fragile analog baseline. The FTU replaces it with the flagship absolute, a mathematical anchor that does not degrade. This diagram shows how a non-decaying metric creates a shared baseline for data normalization. It allows researchers to evaluate measurements using a single absolute scale. When digital computation, AI, and biosonics use this standardized tick, they communicate frequency data using the same zero-drift language. The compounding errors and phase drifts that threaten to crash high-speed networks are bypassed. We can now push processing speeds further because the timing baseline no longer decays. By replacing a physical baseline with a mathematical constant, We've removed the primary source of drift from our most sensitive systems, providing the stability required for the next generation of technology.